Bismillahirrahmanirrahim. Today we shall talk about compositions of transformations or composite transformations. Basically, doing more than one transformation on a particular figure. If you recall, transformations were of four types: translations, reflections, rotations, and dilations. So translation, reflection, rotation, dilation. These are four types of transformations. Translations are also known as slides or glides. Now, if we do any combination of these to a particular figure, for example, you can take a figure and then first translate it and then reflect it, or first reflect it, then rotate it, or dilate it. If you have any combinations of these transformations, that's called a composite transformation or compositions of transformations. I tend to use again the composite transformation because I'm more comfortable with that. I've used that before, but either one of these two terms is perfectly fine. So anytime we combine transformations, that's called a composition of transformations or composite transformation. So here's an example from your book. This is a figure where you have a line L, and you have a footprint there, and you see a second footprint that actually has been slided over, glided over, or translated, it's moved over. So this is an example of a translation across using this particular vector W. So as you recall, you can use vectors for translation purposes. So this is a footprint that has been glided or used to move a particular image across the screen like you see. So this is a simple translation, slide, or a glide. Now you can reflect this particular image, in this case across line L, and that would be a second transformation. So first we performed a slide, and then you performed a reflection. So this would be a slide glide transformation, or glide reflection transformation. So you can first we had a slide or a glide, and then we reflected. So this would be an example of a glide reflection. So that's just an example. And then you can do more with this particular figure. You can translate it again. You can move it across the same vector or any other particular vector, and it will give you that figure. And then if you were to reflect it again, and you would have the footprint again on this side of the line. So you can do many things, and here we didn't dilate or rotate this particular figure, but you get the idea. So anytime you do a combination of transformations is called a composite transformation or compositions of transformation. There's another interesting thing about this particular example you'll see is that we first translated and reflected and translated and then reflected, and you can see and you can imagine that doing all of that was basically moving 2 steps forward, isn't it? Right? So if you were to take this particular figure from here, first go over here and then put another foot over here, it's like basically 2 steps forward. So sometimes when you have composite transformations can result in different composite transformations can result in the same end result. In the first case, we had a translation, reflection, translation, and then a reflection. In the second case, you would have just 2 translations, 1 foot above the other, so to speak. So different transformations, composite transformations can result in the same end image. So this is an example of a composite transformation. Okay, so here's an example from your textbook. Basically, our instructions are to translate triangle JKL. So here's triangle JKL. So we are to translate it or slide it or glide it, whichever we like to. See, we're to translate the triangle JK along this. This is a vector, if you recall, and this is a is component form of this particular vector. So this is a vector in component form, component, component form of a vector. And so we are to translate it and then to reflect it in the y-axis. So we're supposed to do two things over here. First, we are to translate, and second, we are to reflect. So this would be a composite transformation or composition of transformations. So okay, so this vector, the transformation vector, is 0, 4. Remember, you pin the vector to the origin to figure out which direction. So 0, 4 would basically move the whole thing up, straight up like this. So that's what that vector is saying. So we are to move this triangle basically up like this, right? That's the first thing you're supposed to do. Now, as I said, it's always best to be like methodical about these things, so try not to rush it. So let's say J, I'm just going to write the ordered pairs for these. So J is 6, negative 1, and then you're going to use the vector to first translate, and that will become J prime. So pre-image and image J prime. And then let me just write J, K, and L also. K is 10, negative 2. And we're also going to use the vector to give that. And then JKL will be 5, negative 3. And again, we're going to translate that to get L prime. Now, allow me to bring to your attention the in this particular Cartesian plane, each of these boxes is 2. So the 2, 4, 6, 8, because the numbers are a little bigger. So I have to use a different Cartesian plane scale over here. So it's always important, therefore, to label your Cartesian plane so the person knows. If I didn't do that, you'd be all confused, wouldn't you? So, so it's always good mathematical manners to label your axes and each increment that's represented in the Cartesian plane. Okay, all right, fine enough. So here's translate, and we're going to use the vector 0, 4. So simply then, if you recall, you just add the vector components over here to get this the ordered pair. So that will remain 6, and if you add 4 to negative 1, you get 3, and K prime would be I'm just going to be, as I said, I'm just not mess with it, just be a good boy and just write the vector every single time. Anyway, so here it is. So K prime would become 10 and 2, and then L prime would become 5 and 1. There it is. So I'm going to draw this out. So 6, 3. So here's 6. That's 6, 3. So that's J prime. And then I have K prime is 10, 2. That's 10, and that's 2. So that's K prime. And L prime is 5, 1. So that's 5, and 1 is right smack in the middle. L prime. So here's my L prime. So I can draw this out over here. There we have it. So I've basically moved this whole triangle up like that, right? So that's my first part of the job. The second thing now we're supposed to do is we're supposed to reflect this across the y-axis like this, okay? So that's what we're going to do next. So let's reflect it about the y-axis. So to reflect it about the y-axis, I'm going to just do it over here. So we're going to reflect about the y-axis. So I'm just going to write that so I don't make any silly mistakes. Okay. Now if I do that, what I'm going to get over here, if you take each ordered pair. So let's write the ordered pair so we don't make silly mistakes again, because that's the worst thing to do. You know, and people are watching you. Just kidding. It's not a big deal. If you make a mistake, I've done that 1,000 times. Okay, maybe not 1,000 times. So 5 and maybe 1. Okay, so I just wrote them out. So now reflecting means the y coordinate won't change. It'll be the same height, but you just have to take it on this side. The x coordinate would change. So in this case, 6 will become a negative 6. So I'll have a negative 6, and the y coordinate won't remain the change. It will remain the same. It will not change if I'm to reflect it about the y-axis. Cool. So and then K prime will become negative 10 and 2. And L prime will become negative 5 and 1. So this would be like L double prime, and this would become K double prime and J double prime. So I probably should, if I planned it better, I would have put it properly. But anyways, now I'm just going to draw these out. So once I've corrected the axis properly, I'm going to draw these out. So the J double prime is negative 6 and 3. That's over here. That's J double prime, and k is -10 and 2i. That's beautiful, and it's important. -5 and 1. -5 and 1, it is right here, and that is L double prime. Now I'm just going to connect these. There we go. And here we have it. Ta-da! Now, then we're done. See, we first translated using this particular vector, and then we reflected it about the y-axis, and we have our composite transformation. So this particular transformation here is the composite transformation, okay, of the original image, which was over here. All right, so that's a good example of a composite transformation. Okay, so here's another question from your textbook. The instructions are the endpoints of the segment CD are -7 and 1, and D -3 and 2. So graph CD and its image. So I've actually graphed it out for you already. Here's segment CD, graphed on the Cartesian plane. I was making sure also I labeled it correctly. So graph CD and its image after a reflection in the x-axis. So we're supposed to do two things. It's again a composite function. So we're going to first reflect it looks like, about the x-axis, and then we're going to rotate it 90 degrees about the origin. Okay, so we can do this. All right. So the first thing we're going to do is we're going to reflect this about the x-axis. So we can be methodical again, so we don't make any silly mistakes. So I'm going to reflect this about the x-axis. Sorry, that's not the a-axis. So it's about the x-axis. So x-axis. All right. So and then I'm going to do both of this. Here's D. I'm going to write it out. -3 and 2. Now, if you're very careful about it, you don't have to write it out like I'm doing obsessive over here. But you do. The idea being, be careful with it, because people make silly mistakes and do some silly things and get the question right. So if you do first reflect it about the x-axis over here, like a mirror image about the x-axis, this will become C prime. The y value won't change. See, the x value, the y value will change. The x value will remain the same. So this will be -7 and -1. Okay, that's why you have to be careful, because if you don't visualize it carefully, you can make silly mistakes. So it's -7 and -1, and D prime will be, again, the x value will remain the same, the y value will flip. That's D prime. So let's graph this out. So it's -7, -1. So that's C prime, and D prime is -3 and -2. So that's D prime. Okay, so I'm just going to connect the dots. So that's a reflected image. Got it. And then we're supposed to rotate this by 90 degrees. So we have a 90 degrees rotation to both of these. Okay, if you recall, when you're doing a 90-degree rotation, right, if you're doing 90-degree rotation, you like make the y -y, and that will take the place of x, right? So when we do that, what we'll have is you take the y, make it a -1, and put it in place of the x. So this will become 1, and then the x will just shift into the y position, -7, like this. And if I do that again, take the y, make it a negative of a negative positive, that's 2, and the x will take a spot of the y. So that's a 90-degree counterclockwise rotation. In this case, we were not told if it was clockwise or counterclockwise. We assumed, therefore, it was counterclockwise by that's the default situation. So now I'm going to draw this out. 1, -7, that's 1. Okay, that's 4, that's 8, that's -8, that's -6 over here. So -7 is right in the middle. That's going to be C double prime, and 2, -3, that's right here. 2, -3, that's D double prime. So that's D double prime, C double prime. So that's D double prime, and that's a rotated image by 90 degrees. So let me connect the dots if I could do it properly. Here we go. Okay, so come on, my friend. There we go. There you go. So now we did two things. First, we reflected this, And secondly, we rotated this image by 90 degrees counterclockwise. So this is a composite transformation, first a reflection, then a rotation. Alright, so now this section ends with two theorems which are actually kind of cool, but they're reasonably intuitive theorems, which we shall talk about. And the first one is this. This term is called reflections in parallel lines. That is, if you have an object, what happens if you reflect it across parallel lines? Now, we're not translating here, we're not sliding, we're not gliding, we are reflecting like a mirror image. What happens if you like double reflect across parallel lines? That's what this is talking about. So I call this the double reflection across two parallel lines theorem, because that's what you're doing. You're reflecting two times across parallel lines. So then what happens? The theorem says that if you do this, this is what happens. The composition, the composite transformation, the composition of two reflections in parallel lines can be described by a translation. So two reflections across parallel lines can be described by a translation vector. So two reflections basically results in a translation, kind of like the footprints that we talked about. So if you reflect it two times, it's the same thing as a translation. That's what it's saying. So if you reflect two times across parallel lines, it's the same as a translation. But there are two peculiarities about this particular translation vector, or two details that we have to know. First, of course, that the vector is perpendicular to the two lines, because when you move things and measuring distances across, if you reflect across parallel lines, you reflect in a perpendicular distance. So obviously, you have to be vector has to be perpendicular. Secondly, which may not be as intuitive, the length of the vector is twice the distance between the two lines. Now, what does that mean? So let's see what happens here. So if I take this triangle P, this particular object that they have labeled as triangle P, if I reflect it across the first of the two parallel lines, this is line K, if I just reflect it, mirror image it, I'll get that. I'll get this triangle, the green triangle P. Now, here we're going to double reflect it. We're going to reflect it again. Now we're going to take this image P prime and going to reflect it across the line L. When we do that, we get something like this. That's P double prime. So we've taken one image, this particular triangle, and we reflected two times across parallel lines. Now, if you notice the first image to the last image, they look they're similar. It's like the one big translation, and that's exactly what it is. So two reflection basically means one translation, or gliding or sliding the object. That's fine, but the distance, how much? By how much? The distance ends up being, in fact, twice the distance between these two parallel lines. Okay, now what does that mean? So watch. If you take a vector that translates the first blue triangle to the red triangle, the vector would look like this. Okay, so that's the vector that's translating the blue triangle to the red triangle. So of course, you would take every vertex of the triangle and translate it and connect the dots. Sorry. Of course, and you do it across perpendicular distances, right? That's what the theorem says. So it's like translating with the vector that's perpendicular to these. And then the distance, what's the length of this vector? If you remember, a vector has two components. You have to say the length of the vector, and you also say the direction of the vector, right? So this vector is perpendicular to these lines, and how far do you translate? And that's the concept that may not be readily intuitive, and that is the distance is actually twice the distance between the two lines. That is, if you measure the distance between two lines, of course you measure distance between lines, perpendicular distance, of course, right? So the length of the vector is two times the distance between these two parallel lines, and that's a very beautiful theorem, and which suggests that double reflections across parallel lines is the same thing as a translation, and that translation with the vector that's perpendicular to these two lines, and the length of the vector is twice the distance between these two parallel lines. I think that's a very beautiful theorem. Okay, so the final theorem in this section is the following. This theorem is also very interesting, I think, and the theorem basically states that if you reflect an object across two intersecting lines two times, then that's equals to a rotation. So this is also about a composite transformation. So precisely the theorem is about reflections in intersecting lines. The way I remember is a double reflection in the intersecting lines equals rotation. So double reflections across intersecting lines equals a rotation. The composition of two reflections in intersecting lines can be described by a rotation. So if you do two reflections and that across intersecting lines can be described by a rotation. So if you have for example, a object here, here's a segment, they call it segment A in your textbook, and we shall respect that. So that's a segment A. And if you reflect this two times across these lines, and that's like a rotation, that's what it's saying. And what kind of rotation? Rotation precisely is about across the point over here of intersection. So the rotation will be across the point of intersection. And secondly, the angle of rotation will be twice the angle of that's formed by the intersecting lines. So the rotation will be about the point of intersection and through the angle that is twice the measure of the acute or right angle formed by these angles. Now, what does that mean? So first, if I were to reflect this segment A, first across line K and then across line L, that is, I'm just reflecting across two intersecting lines. So first I reflect across line K and I would get A prime, the image A prime. Then if I do a second reflection, that's a double reflection, across the other line, line L, I get this particular image. So now I have done two reflections, first across line K, and then I have reflected the image A prime across line L to get a double prime. So those are the two reflections we're talking about. Now these two reflections, this theorem says, would be effectively can be accomplished, or you can do the same thing if you were to, instead of double reflection, if you would do a single rotation across point B. And by how much angle? Because you rotate across certain an angle, right? You rotate across any angle, whether it be 60, 120, 55, or 90 degrees, 180, etc. So we have to know by how much are we rotating the object. Well, the angle of rotation in this case is going to be twice the angle that's formed by the intersecting line, the acute angle, or up to a 90 degrees angle that's formed by the intersecting lines. So the angle of rotation will be twice as big as, in this case, 2x. So if the angle between the two lines would be x, the angle of rotation of the object, in this case A, would be 2 times x to get the final rotation. So again, if we were to reflect object A across K and then reflect it again across L, we get A double prime. You can get the same thing by doing a rotation like this. You can rotate across that point P all the way across by the angle measure that's 2 times the angle of x, and that's what this theorem states. The theorem states specifically the composition of two reflections in intersecting lines can be described by a rotation. That is, double reflections across intersecting lines is the same as a rotation about the point of intersection and through the angle that is twice the measure of the acute or right angle formed by the lines. And that's a pretty interesting theorem as well. Now these theorems are kind of little exotic theorems. They're fun to know, and perhaps you'll find them useful, and it's just kind of fun. Mathematics is just sometimes very interesting, and it can be fun just because it is, and I hope you appreciate that. Until next time, assalatu wassalamu ala rasulillah walhamdulillahi rabbil alamin. Assalamu alaikum.